All right, so here we're going to start in on section 7.4. We're going to start in with fluence. So fluence is going to be the capital letter phi. So it's n divided by a. Now, what do those two variables mean? N is going to be the total number of particles entering a sphere of small cross-sectional area A. Now let's find section or figure 7.2 to give us a better idea as to what's going on. So you got all of these little particles going this way and that way and whatnot. How many of them are cutting through this cross-sectional area? That's the idea of fluence. And you can see it's not necessarily cutting through the center there. It's just whatever so it's not necessarily the radius. What we're looking at is just a cross-sectional area of that particular sphere. So the particles could be photons, electrons, neutrons, whatever. The units of fluence are going to be found from the definition. So basically it's a number which really doesn't have much of a measured quantity associated with it, or unit, I should say, divided by area. So basically it's going to be meters to the -2 power or centimeters to the -2 power, whatever the area measurement needs to change to in order to be able to help our computations. Energy fluence, it's the same thing as particle fluence, only you're dealing with the energy. So E sub T is the total energy carried by all particles entering a small sphere of cross-sectional area A. So psi is going to be the capital letter here used to represent that. So phi is for the particle fluence. Psi is going to be for the energy fluence. The units of the energy fluence are joules per meters squared. Since we're dealing with the amount of energy that's going in, the amount of energy is, in this case, joules. It's not like the particles that we had was just a number. So for a monoenergetic beam, the total amount of energy here is going to be whatever the energy is of the photon coming in times the number that you have. And psi is going to be E sub T divided by A, or E sub gamma times N divided by A, or basically the energy of the photon times the fluence. The energy transfer coefficient, or mu sub TR, that's what the TR is there, associated with transfer, is a fraction of the photon energy that is transferred to kinetic energy of charged particles per unit thickness of absorber. So the energy transfer coefficient is going to be the mean amount of energy transferred divided by the energy of whatever the photons happen to be, multiplied by mu. And the mu, of course, is the linear attenuation coefficient. So you got the linear attenuation coefficient, you got the amount of the average kinetic energy transferred to an electron divided by the total energy that's coming in. For Compton scattering, this is the average energy transferred to an electron from a photon of energy E sub gamma. Notice that the transfer energy transfer coefficient is going to be less than the linear attenuation coefficient, because a photon cannot give up all of its energy to an electron in Compton scattering. And therefore, this ratio is going to be less than 1, which you can do a little math here and you can kind of see that. The energy absorption coefficient is going to be defined as this. So you've got either energy that's being transferred to an electron, or you've got energy that's being absorbed. And so you've got the absorption coefficient, and then you've got the transfer coefficient, energy transfer coefficient, energy absorption coefficient. So electrons can lose energy via two mechanisms, either by collisions, which lead to ionization and excitation, or radiation that is lost to the local region. And recall that in the radiation yield is a total fraction of initial kinetic energy emitted as electromagnetic radiation when a single electron slows down and comes to rest. When the electrons are set in motion by photons, they start off with a variety of values of initial kinetic energy. The average value averaged over all values of starting energy T sub naught, is given by the symbol G. This is the fraction of the initial kinetic energy of all electrons set in motion by photon or radiation that is lost to Bremsstrahlung as the electrons are brought to rest in the medium. So there's a relationship between energy absorption coefficient and the energy transfer coefficient. So the amount absorbed here is going to be equal to the energy transfer coefficient times 1 minus G. And this reflects the fact that some of the fraction of the transferred energy is irradiated. Often G is going to be small, and therefore they're pretty close to each other. So for cobalt-60, you can see here the value of G is 0.0032, and for 100 to 135 keV X-rays, it's even smaller. So that's why they say that these values are pretty close to each other. So a very important quantity in radiation physics for indirectly ionizing radiation is called kerma, which is an acronym for kinetic energy released per unit mass in a medium at a specified point. And the definition of kerma is this, where E sub TR is the sum of all of the initial kinetic energies of all charged particles, generally electrons for photon irradiations, and protons for neutron irradiations. And this is liberated by uncharged ionized particles in a material of mass m. This is not the same as this. The units of kerma are going to be joules per kilogram. This combination of units has been given a particular name. You may remember it from the summary. It's called a gray. The value of the kerma at a particular location may not be a measure of biological damage there, because it doesn't necessarily tell us how much energy is absorbed at that spot. Note, not all of the energy is retained locally. Some of it's radiated by Bremsstrahlung emission for the charged particles, and the charged particles move off to a different locality. The tracks of the charged particles produced may be appreciable in length. Therefore, energy transferred to charged particles at a particular location may be absorbed elsewhere. An alternative but equivalent equation for the kerma in terms of energy fluence is going to be this, where mu sub TR bar is the average value of the transfer energy coefficient averaged over the spectrum of incoming photons. Kerma can also be written as a sum of the collision and radiative kerma. The collision kerma is energy transferred to charged particles that go on to produce excitations or ionizations. The radiative kerma is the energy transferred to charged particles that ends up being radiated. So you got all of kerma, and then you've got the collision kerma, and then you've got radiative kerma. Collision kerma is defined as this. Radiative kerma is defined as this. One of the most absorbed quantities in radiation therapy dosimetry is going to be the absorbed dose. It's closely related to biological damage because it's the energy actually absorbed in the medium at a specific location. This is the definition. E sub AB is the total energy absorbed from indirectly or directly ionizing radiation inside a small mass of material. The units are joules per kilogram, same units as kerma. The gray is obviously used as the SI dose. 1 rad is equal to 100 ergs per gram. The erg is an antique unit of energy. We don't really use it anymore. In the old days, physicians were accustomed to writing radiation dose and prescription of rads. When told that they needed to adopt proper SI units, many of them simply wrote down the same numerical value for the dose. Instead of following this with unit rad, they wrote centigrade. So the dose may vary from point to point in the median, and a radiation therapy prescription must not only specify the dose to be delivered, but also precisely where it needs to be delivered. So there's a relationship between dose and collision kerma. Recall that the collision kerma is the energy transferred to charged particles per unit mass that ultimately is absorbed via collisions, as opposed to Bremsstrahlung. After the energy is transferred to the charged particles, they move off to another location where they deposit this energy. That is, the energy is absorbed. So if CPE prevails in a given region, then for every charged particle that carries its energy out of the region, an identical charged particle will enter. In this particular case, when CPE holds, the dose is equal to collision karma. So as described at the beginning of chapter 6, absorption of energy from indirectly ionizing radiation, photons or neutrons, is a two-step process. First, you got to liberate the charged particles. That's related to karma. The second step involves the absorption of the energy of the charged particles, and that's related to dose. So you got your photons or neutrons, then you got karma going on. That liberates charged particles. Then you've got dose, which is going to end up being deposited somewhere, and we're looking at the local amount that is deposited. So let's say you got a beam of 10 MeV photons interacting with water in some small volume of the water at a particular location. The fluence is this, and mu divided by rho is going to be this. Mu of TR divided by rho is this, and mu En divided by rho is this. So what is the energy fluence in terms of joules per meter squared? The energy for mono energetic photon, which is why they give it to you to ease the calculations a bit, is going to be this. If you know that we're dealing with 10 MeV, so we're changing that to 10 to the 7th EV. Then we're doing an energy conversion here, and so we have this number of joules, and therefore the energy fluence is going to be 1.65 times 10 to the minus 12 joules times this amount of cross-sectional area, and so we end up with this energy fluence. So what is the average energy transferred to an electron by a 10 MeV photon? All right, so we've got the average E sub TR is equal to the electron energy multiplied by mu TR divided by mu. We take those both, and if we divide them by rho, we have those values here multiplied by the energy, and then we end up with the average energy transfer. What is the average energy absorbed by the water per photon interaction? Well, we'll use this particular formula. Again, we have these particular values here. We substitute them in, and we come up with this. So why is there a difference between the answer to part A and part B? And where does this missing energy go? So not all of the energy that is transferred to electrons is absorbed. Some of the transferred energy is radiated away as bremsstrahlung. So we have E sub TR, which we found up here, minus E sub AB, which is what we've got here. So this is the amount transferred. This is the amount absorbed. So the difference here is going to be 0.2. So what is the value of G? 1 minus G, you can follow back to equation 7.9, is going to be equal to this. If we divide both by rho, which we have those values for, then we can figure out what 1 minus G is. Solving 1 minus G is equal to this. Solve that for G, we come up with this. So note that the energy loss to bremsstrahlung divided by the average energy is this value. So what is the value of the collision karma expressed in gray? Collision karma is calculated by equation 7.13. We need to use a consistent set of units. So we've got to make sure that we change all of these conversions here. So we're changing all of this to meters squared per kilogram, which is why we went through those exercises earlier. So mu sub En divided by rho is going to be equal to this, and collision karma is going to be the product of these two. We've got this value here for psi. We now have the value of mu sub En divided by rho, and it equals 1 gray. If there is CPE in a given volume, what is the absorbed dose within this volume? The absorbed dose is equal to the collision karma, which if you remember that equation that we went over, that's what it's talking about since CPE applies. And then therefore the dose is equal to 1 gray. All right, we'll start up section 7.5 in a different recording.